heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world. All right, good evening and welcome everyone to Mount Washington Observatory's Science in the Mountains program. My name is Brian Fitzgerald and I am the Director of Education here at Mount Washington Observatory. Thanks so much for joining all of you this evening. Looking forward to tonight's program tonight, where we'll have an update on two newly launched research projects here at Mount Washington Observatory with interns Henry Moskovitz, Naomi Lubkin, and Larz von Huene. Thanks so much again for joining tonight's program. If you're not already familiar, the observatory here is a nonprofit member-supported organization with a mission to advance the understanding of the forces that create Earth's weather and climate. And the way we do that is by running our weather operations with our around-the-clock Summit Weather Station, our White Mountain Mesonet, by conducting research and product testing projects, and by delivering and offering innovative educational programs. If you have questions, as always, for tonight's speakers, and you're joining us on Zoom, you can use the Q&A button, which you can find just at the bottom center of your screen. And feel free to submit those questions whenever they pop up tonight. And we'll make sure we leave time at the end of both sessions. All the way at the end, we'll make sure to do a Q&A session this evening. So get your questions in whenever they come up. If you're joining us on Facebook, welcome. Thanks so much for joining that way. We won't be able to answer your questions in real time tonight during that program. However, if you'd like to have your questions answered live during any of our upcoming programs, make sure you join us on Zoom. You can register over at mountwashington.org/SITM. All righty, so while we kick things off this evening, before we get our presenters here on the screen, I will launch a quick poll just to show a few questions. Love for all of you who are joining on Zoom to participate if you would like. You'll see some questions popping up on your screen now if you're joining us through the Zoom program. 4 questions for you this evening. We're curious, hey, where you're joining from this evening, perhaps a state within New England here, perhaps outside of New England, or perhaps even outside the country. Welcome to all of you again this evening. Always curious, always amazed to see that we have newcomers every month to our program here. And I'm curious, how many Science in the Mountains programs have you watched? Maybe this is your first one. Maybe you've seen a few, maybe quite a few. Maybe you're here just about every month. Love to know how folks are participating. And then we have 2 questions, one each from our presentations tonight. The first one being, what is a near surface lapse rate? Is it a change in temperature over elevation alongside a mountain slope? Is it a change in solar intensity over time? Is it the rate in which lava cools? Or is it a change in temperature over elevation in the free atmosphere? And last but not least, what determines tree line on Mount Washington? Is it the mean maximum summer temperature? Is it the lack of oxygen at elevation? Does that have something to do with solar intensity? Or is it a big combination of things like, say, temperature, physical barriers, exposure, combination of other weather conditions? Choose wisely here, and we will have our speakers certainly cover these answers and more in just a little bit. So I've seen quite a few of you participating. I'll give it just a few more seconds here, and we'll show some results in about 3, 2, 1. All righty, stop the poll there and we'll share some results. Looks like tonight, the Granite State is just being edged out by folks outside of New England at 28% of our participants so far on Zoom tonight. Great representation all around New England, and even have one person joining us from outside the US of A. Welcome, welcome. Thanks so much for joining tonight. For those of you, a nice mix. Wow, look at this. How many people have joined Science in the Mountains programs before or watched perhaps some of our recordings? Wow, 16 of you, 21% are watching your very first program. Well, welcome. Glad to have you on board. Hope you'll join us for another program in the future here. And a nice mix and a special shout out to those people who said they almost never miss it. I was reticent to even put that as an answer, but you know what? I'm so glad I did. Thanks so much for those of you who continue to follow along with the program here. All right, and our trivia question, what's a near surface lapse rate? Well, almost a even split between, is it a change in temperature over elevation alongside a mountain or in the free atmosphere? We'll find out later from Henry. And the last but not least, well, overwhelmingly 90% of you thought a combination of temperature, physical barriers, exposure, and other weather conditions lead to determining tree line on Mount Washington. Well, we'll have to find out a little bit more about that one just a little bit as well. So I'll go ahead, I'll stop sharing that, and I would love to introduce our first speaker for this evening, Henry Moskovitz, who is the summit intern on one of our 2 shifts on the mountain this summer. Henry, hey, how's it going?
It's going well.
Hey, thanks so much for joining us tonight, and thanks so much for offering to present on the research project that you helped kick off this year. I can hear you and see you just fine, so by all means, feel free to take it away.
All righty. All right, so hello, sorry, let me just get one thing set. All right, hi, I'm Henry Moskovitz. I am a senior at Embry-Riddle Aeronautical University studying meteorology, and this summer I was one of the interns at the Mount Washington Observatory. As an intern, I helped out with day-to-day operation of the observatory. I learned how to forecast for the higher summits. I got to help with hourly weather observation, give tours to supporting members of the observatory, go on sunset hikes, and of course, I worked on a research project, which is what I'm here to tell you all about. All right, so this summer, I worked under the supervision of Jay Broccolo on a project which will be continued by interns throughout this year and is planned to be finished in the spring. The title of this project is Establishing Baseline Seasonal Near Surface Temperature Lapse Rates on Mount Washington. And our hypothesis is that near surface lapse rates will vary from free air lapse rates, changing with the season and varying on windward versus leeward sides of the mountain. All right, but before I get into everything, just a little overview of what I'm going to talk about today. So first of all, in kind of answering that poll question, what are lapse rates? Also, what differentiates a near surface lapse rate? Why do they matter? How will we be establishing lapse rates? What have I done on this project? And what will this project look like going forward? All right, so to start out, what is a lapse rate? I believe answer A was correct for what is a near surface lapse rate, but a lapse rate in general is just a change of something over some increment. And for what we're doing, we're talking about temperature lapse rates in the atmosphere. And so that's the change of temperature as you increase elevation or increase your height in the atmosphere. So this chart here on the left, this shows the average lapse rates through the different layers in the atmosphere. And the atmosphere is kind of like a layer cake. And each layer is defined by an average rate of change of temperature. And for this project, we're mainly concerned with the troposphere, which is the lowest layer of the atmosphere. And the average lapse rate for the troposphere is 6.5 Celsius degrees per kilometer gained, basically. However, the problem and the reason we're doing this project is because in regions like the White Mountains, where you have a lot of complex terrain, temperature might change in a way that is not very predictable or doesn't follow this global average, and it could be very different. This slide, for instance, kind of points this out. This was an event last winter where there was a blast of cold polar air that came down over the Northeast, and temperatures in most locations fell to below 0. But actually Mount Washington, which is circled in red here, was actually the warmest spot in New Hampshire, and I think most of the region as well. And this is kind of backwards to what you might normally assume, because normally we find that as we climb up a mountain or go up in the atmosphere, temperature gets cooler. So why is this happening? So there are a combination of variables, surface and atmospheric processes that can basically make a near surface lapse rate variable. And so I've got a list of these things below. So albedo, that's just a fancy term for how reflective is your surface. So for example, a snow-capped mountain, that will be very reflective. And so it's not going to absorb as much of that sunlight, and it's not going to heat up as much on top of the mountain. However, a darker surface down below, say below tree line, might absorb the sun better and heat up much quicker. And then when spring rolls around and all that snow starts to melt, that will also affect the temperature. So the near surface air over the melting snow will actually generally be held near that melting point, being 32 degrees Fahrenheit or 0 Celsius. And then cold air pooling. This is a cool phenomenon that I like that's found in the mountains. So on calm, clear nights, the surface will cool faster than the upper air. And what this does is it makes the near surface air become colder and more dense. And then it flows down the sides of the mountain, sort of like streams, and then pools in the valleys. And this can lead to situations sort of like what I showed in the previous slide, where you have colder temperatures in the lower elevations and warmer temperatures aloft. Additionally, the tops of mountains can be exposed to the free atmosphere being the atmosphere that's normally not influenced by the surface. That and also unique wind patterns in the mountain can influence temperature quite significantly. So I've said all that, and you might be just sitting there thinking to yourself, okay, so why should I care? Well, trust me, it's important. So temperature is super fundamental to most processes that occur in our environment. So temperature affects the weather. It affects species that live in alpine environments. It affects whether you're going to get snow or rain and how fast that snow will melt. Take the western half of the United States, for instance. Even though not everyone lives in the mountains, they're super dependent on the snow in the mountains for a source of water. And again, temperature affects how much snow will accumulate and how fast it's going to flow out of the mountains. And so that's an important thing that we're going to want to know if we want to know where our water is going to come from. So we're interested in how temperatures are changing. And so in my research this summer, I was reading Georgia Murray's recent research that she conducted with some colleagues. Georgia Murray actually is working for the AMC, and she found that there was different rate of warming at the base of Mount Washington to the summit. And so this is something that will affect lapse rates. And so basically what this means is if the base of the mountain is becoming warmer at a faster rate than the summit, you're going to get a steeper lapse rate. In other words, more cooling going up the mountain. And that the rate of cooling that you get affects the type of weather that you're going to have. Are you going to have clouds, rain, snow? All of that is affected. Can't say it enough, but lapse rates are very important. So basically, this rate of warming is super related to this project and something that we will continue to consider. So temperature is also related to precipitation, as I was starting to allude to there. And precipitation is just a fancy word for something falling out of a cloud. So whether that be rain, snow, hail, those are all precipitation. And the way this works is that in an atmosphere that is warmer, it's able to support more water vapor. And this is kind of like having a sponge and having a bigger sponge. With the bigger sponge, you can absorb more water. And this chart on the left here, this plots basically just what I'm saying here. And what this shows is that not only can a warmer atmosphere support more water, but as the atmosphere warms, it can support exponentially more water. So this can lead to a couple of different outcomes. So this can seem a little counterintuitive, but a warming environment can lead to an increase in droughts and floods. And you might be wondering, like, shouldn't it be like rain or not rain? But it makes sense that they go hand in hand, because if you think of it back to that little sponge analogy, if you have a big sponge, it's going to be hard to saturate it. It's going to be hard to completely fill it with water because it can absorb so much. And so that if the atmosphere can absorb a lot of water, it can lead to droughts. But on the other hand, if you are able to saturate that atmosphere and then have a rain event, you can have super intense or more intense rain events that lead to flash flooding. And so these pictures that I have on here are from this summer. This is a map of drought across the US. And on the right, this is a picture of flash flooding that occurred in Yellowstone National Park also this summer. So as meteorologists and just generally earth scientists are very interested in temperature. As meteorologists and on Mount Washington, we often use this model known as the North American model. And this model comes in a 3-kilometer resolution, which for weather models is actually pretty detailed. However, even if your grid spacing is 3 square kilometers, this is actually not enough to account for all the temperature variations that we get in complex terrain, because there can be completely different temperatures down in a valley versus up the mountain. It changes over very small spaces. And when you're trying to model things like how fast snow will be melting, you really need to be able to account for the different temperatures over those very small spatial increments, and also over short time scales as well. So this is what brings us back to lapse rates. So if you use a lapse rate, which, just as a reminder, is the change of temperature with increasing height or elevation, you can use a lapse rate, and often what has been used is this 6.5 Celsius kilometer to like fill in the dots in that square where maybe we have some average temperature, and you want to like fill in the details in between over that complex terrain. You can use a lapse rate to say at these different heights, we're going to have different temperatures within this grid box. However, if we're using a lapse rate that's not particularly representative of the actual lapse rate on said mountain, you could introduce error into your modeling. And so this is why we want to establish more accurate lapse rates on Mount Washington. So what we can do with Mount Washington is we've set up a system called the Mount Washington Regional Mesonet. This is a network of remote weather stations that we can record data with. And we also have what we call the Autoroad Vertical Temperature Profile, which is a network of stations spaced at 1,000-foot increments along the Mount Washington Autoroad. And those stations are constantly recording data, and we can use that data going up the mountain to calculate a more representative lapse rate. So this summer, I've just been getting this project started. So I've been basically doing a whole lot of reading. So I've been reading studies by other folks and seeing what their findings were and trying to collect information so that I can write an introduction and basically say, here's what other people have found. And so this is what we're going to be looking for in our location. And so I pulled up some charts here that are from some research papers that I've read this summer. This chart on the left, this shows variation in lapse rates over a year. And it looks like a bunch of squiggly lines, but all I want you to notice is that over the course of the year, the lapse rates vary. So here, going into the winter, the lapse rates look like they become a bit more shallow, and then coming back out of the winter, they approach more of that average of 6 Celsius per kilometer that I was talking about before. So I can harp on it all day, but near surface lapse rates can be very variable. Another thing that can influence lapse rates is the wind. So one side of the mountain, the windward side, that's the side that faces the wind. That might have one lapse rate, and the lee side, the downwind side of the mountain, could have a slightly different lapse rate as well. And this can be due to different processes that occur in the mountains that cause clouds to form on one side and the other side is more dry, and this can affect temperature. But this chart on the right here, this basically just shows that other people have observed this variation, and these different lines are sensor set that are set up on different sides of a mountain. And again, all I want you to notice is that there's differences in the lines, meaning that they observed differences in the lapse rates from the different sides of the mountain. All right, so towards the end of this summer, I pulled just a little bit of data from our Mesonet. I took high temperature data for fall 2021 and did some simple math on it to calculate our lapse rate. And I calculated a lapse rate of 6 Celsius per kilometer, which is about average. But the one thing I want to point out here is that this was just kind of a quick thing I did just for fun. There's a lot of quality control things that will need to go in. And this is only one little bit of the data that we're going to be looking at. We're also going to be looking at the lapse rate for daily highs, daily lows, and then using that to calculate average lapse rates for the different seasons. So going forward, our future interns are going to be doing a lot more with the data to actually get into kind of the meat of this project and actually calculate and find what we want to know. All right, and so that is about to wrap it up. So just for my conclusion here, so as I've been saying, near surface lapse rates are super variable. And since we have all sorts of systems within our environment that are highly temperature sensitive, if we want to understand everything that's going on in our complex alpine environment, and additionally how it might change so that we can be better prepared for any of those changes, we need to understand the distribution of temperature. And that's what we hope to use lapse rates for. So moving forward with this project, we'll test our hypothesis, looking for statistically significant differences in near surface lapse rates from free air lapse rates. And this last one, this is just my references in case you wanted to see that. All right.
Excellent. Well, thank you so much, Henry. Appreciate you showing us all your work so far here. Really excited to see not only what you've done so far, but certainly where the project goes from here. I know a number of staff are really appreciative of your work so far this summer. Thank you. If you have questions for Henry, Henry's going to disappear just for a little while so we can go move on to our next presentation, but we will take questions for both Henry and Naomi and Larz at the end of both presentations here. So if you have questions, please make sure you use the Q&A button that you find down at the bottom of your Zoom toolbar there. All right, so let's keep things moving along here. Let's hear from our next set of presenters, Naomi and Larz. I know you're both on the summit of Mount Washington right now, and whenever you're all set, feel free to come online and hey, how's it going?
Hello.
Thanks so much for joining. I know you cut out of Summit Crew dinner just to be able to join us tonight, so thanks for doing that. Well, without further ado, I introduced you a little bit before, but Larz von Huene here is our AMC intern who's spent quite a bit of time. It's been very convenient because Larz has been at Lakes of the Clouds this summer, so has been at least our closest neighbor that we could possibly have here just about on the summit. And Naomi Lubkin, our intern on the opposite shift from Henry. So Naomi, Larz, without further ado, why don't you take it away?
All right. So hi, everybody. Welcome to our presentation on humidity and wind and their combined effects on tree line and exploration. So I'm Naomi, one of the Mount Washington Observatory summer interns, coming to you live from the summit of Mount Washington tonight. I am from Bartlett, New Hampshire, and I'm about to go into my 4th year at the University of British Columbia, where I study biology. As an intern at the observatory, I live up here for a week at a time, and while I'm on the summit, I help out with various daily tasks and summit operations. I shadow observations, I've learned how to forecast for the higher summits, and I give weather station tours to observatory members. And I've also been working on this research project.
And I'm Larz, doing a research internship with the Appalachian Mountain Club, or the AMC. And I am living down at Lakes in the Clouds hut, where I spend my time doing hut jobs, such as making dinner and breakfast, but also taking cloud samples and watching the plants grow. I just graduated from Smith College with a degree in biology and landscape studies. And I'm going to continue on with this internship through the fall before I head off to Europe. So this project was funded through the Waterman Fund, which promotes education, trail rehabilitation, and research in the White Mountains, as well as other alpine areas in the Northeast. This is the first leg of this project, and it will be continued on by future research interns of the observatory and the AMC, and potentially by me and Naomi as well. The overarching goal of the project is to develop climate indicators related to damaging events, such as wind, temperature, and relative humidity.
So the main question we've been trying to answer with this project is, what are the long-term wind speed and moisture trends on Mount Washington, and how might changes in those trends affect tree line? So we're aiming to assess any shifts in relative humidity and wind speed over the last 80 years and potential implications of these shifts. We expected that wind speeds will continue to decline slightly, relative humidity will continue to remain relatively unchanged, and as a result, if anything, damaging events will slightly decrease. If this is true, we could expect an upward shift in tree line due to a decrease in damaging events, and therefore a less harsh environment for the alpine vegetation as trees block light.
So what is a tree line, and why do we care about them? So a tree line occurs where trees are no longer able to grow above a couple meters tall. So in this picture, you can see the red line indicates where the tree line is. This is on Boot Spur in the presidential range of the Whites. And this is actually one of the lowest tree lines in the Whites, and it occurs around 3,300 feet. You can see below the red line, there's significant tree coverage, but above the line, there's hardly any, and it's mostly rocky. In the White Mountains, tree lines occur at a range of elevations, starting from that 3,300 feet to around 5,000 feet. And overall, the Whites have some of the lowest tree lines in the world, which is due to the harsh weather that occurs at these high elevation, along with other physical barriers such as boulder fields, like we see in Mount Washington. High wind speeds, freezing fog, and other conditions work together to cause limb damage and prevent growth on trees, resulting in an environment that is predominantly populated by small alpine vegetation. The trees that have managed to survive this extreme environment, though, tend to grow in specific formations, one of which is crummelts, which are windswept patches of trees that have stunted growth due to the high winds. And another one is flagging characteristics, where trunks lack limbs facing into the prevailing winds because of the rime ice and high winds that prevent growth on that side. So Tree lines, because of how they originate, serve as a great way to assess climatic shifts. An upwards shift in tree line, for example, may result from increasing temperatures, but also a decrease in harsh weather events, which would allow conditions for them to grow. Shifts in the tree line can have drastic impacts on the ecosystem because the alpine zone covers, on the grand scheme of things, a very small territory. Me and Naomi looked at a statistic earlier. I think it was 10 square miles.
Yeah.
So upward shifts in tree line could reduce the alpine zone area and could cause the endangerment of rare species living there, such as Diapensia, Lapland rosebay, and dwarf cinquefoil, all which are pictured here. So now that we know that tree lines here are defined by the mechanical damage caused by mountains and intense weather, we're going to look exactly into what causes this mechanical damage. But first, let's define mechanical damage. Mechanical damage is physical damage that is caused by weather events, such as abrasion to trees, stripping of their bark, or the prevention of new growth due to that harsh climate. It's hard to know exactly what combination of weather causes mechanical damage, but we know that wind, fog, and temperature are major players. These three things cause the formation of rime ice, which we'll talk more about later. To try and figure out what level of wind, humidity, and temperature actually need to occur for damage to be done to trees, we first looked to case studies where we knew for sure that the mechanical damage that was happening had occurred due to an extreme weather event. So here's the two case studies. In the first one on the left in 2019, there's an event with extremely high winds. You can see the peak gust was at 171 miles per hour, and the daily average wind speed was also over 100 miles per hour. The environment also had blowing snow, which was causing abrasion to trees above the snowbank, which we can see in the next picture. Overall, there was a lot of damage done in this event. The second case study, the winds were lower, almost half of what they were in the 2019 event. But damage was still done because the temperatures were freezing and it was in the clouds, so glaze ice was able to be formed and cause damage to trees. So in conclusion, these two events give examples of how high winds can be damaging on their own, while lower winds combined with moisture can also be extremely damaging. And later on, we're going to talk about how we examine the frequency of potentially damaging events throughout the years. But first, we're going to dive deeper into what makes these events damaging: wind and moisture. And here's that image from the 2019 event. You can see above the snowbanks, all the trees are stripped of their bark. And that's due to that blowing snow.
So now that we've talked about how the combination of wind and moisture can cause damage to vegetation, we'll break down those events into their two components, starting with wind. The first goal of this project was to update the long-term wind record through 2021. The Mount Washington Observatory is the only source of climatological data for the Northeast's highest mountains. So analyzing this data is key to understanding climate trends in the region. And our database stretches back to the 1930s, so a long-term analysis is possible. The last time the wind record was updated was with data through 2011. And so I started by updating the wind record with the last 10 years of data. And the results of that update are shown here. So this plot shows average hourly wind speed over time, starting in 1981. And you can see that the wind speeds recorded on the summit have not changed significantly over the last 40 years. This is also backed up by the statistics shown in the top right. A send slope is a way to detect trends up or down in data. So a positive send slope would tell us that wind speeds are increasing, and a negative slope that they're decreasing. And this send slope is negative but near zero. And then the high p-value is telling us that the slope is not significantly or not statistically significant, or more simply that the slope is not different than zero. And the last wind update actually found a slight decrease in winds. And you can see that with data just through 2011, so ending right about there, if you can see my mouse, there does appear to be a decrease. But with the additional 10 years of data, you can see that the line has evened out. However, you may have noticed that earlier I said the observatory's data goes back to the 1930s, and this plot starts in 1981. So there's lots of data that we're leaving out here. Next, I'll talk a little bit more about why that is and what I've done to try to utilize that earlier data in this analysis. The Mount Washington Observatory has been operating on the summit and recording wind data up here since 1932. However, in that time, the specific location that instruments are housed has changed a few times, and the instruments themselves have changed as technology has advanced. The image on the left here is an aerial photo taken in 2011, and each number shows a different place that winds have been recorded in the observatory's 90-year history. Since 1981, winds have been recorded on the top of the tower in the Sherman Adams building, and the tower is number 5 on the image on the left, and the top of the tower with the wind instruments is shown on the right. And for the 40 years prior to that, they were recorded in the old observatory building, which is number 2 on the image on the left and has since been demolished. So although the observatory's data set goes back to the 1930s, it's only continuous going back to 1981. And wind speeds recorded from the top of the tower are on average a bit higher than in the previous location. You can actually see why that is in the aerial photo on the left. The tower has no upwind obstructions for winds coming in from the north and the west, which are the prevailing wind directions on the summit. To talk a little bit more about wind speed, this slide shows wind roses for each chunk of time that we've broken the location changes down by. So the circle you can read the same way as a compass rose, where wedges to the west indicate westerly winds, to the north, northerly winds, etc. And the farther from center each wedge goes out, the more frequently winds come from that direction. So for example, the wind rose on the far right shows that 40% of the winds between 1941 and 2021 came from the west, 20% from the northwest, and the other directions had lower frequencies. And these 3 wind roses side by side really show how location matters when measuring wind. While winds in all 3 locations come mostly from the west and northwest, you can see that in the first time period, they were skewed heavier northwest, and in the second, heavier west than in the current location. And to tie this back into tree line briefly, you can imagine that if there's this much variation just on the summit cone, there's also a great deal of variation when you get into more rugged mountainous terrain. The exposure that certain areas get, as well as the side of the mountain trees are on, have big effects on tree line. For example, if winds are mostly westerly, then trees on the west side of the mountain will likely be located lower down or have more mechanical damage than trees on the east side that aren't getting bombarded by high winds as often. And these changes over the years pose a problem when we're trying to analyze the entire wind record. This plot shows a visual of how distinct the differences in wind speed are between locations. So this first split is the switch to the new observatory building in 1941. And this one here is the switch to the Sherman Adams building in 1981. So although we have data going back to the 1930s in its raw form that you can see here, that early data isn't really comparable to the data since 1981 because of these distinct splits. So another goal of this project has been to homogenize the data, which just means adjusting the historic data to make it comparable to the current data based on accepted statistical methods. So as you can see from these averages, the post-1981 winds are about 5% higher than the pre-1980 data. So I did an initial homogenization by multiplying that earlier 40 years of data by 1.05. And this makes the data comparable and allows us to look at wind speed trends over the past 80 years instead of just the last 40. And this plot shows the average monthly wind speeds since 1941, so with the homogenized data. And it allows you to see seasonal and monthly trends in wind. You can see that the winter months have much harsher winds, with October through May experiencing the highest wind speeds. And these are the months that we focused on for the rest of the study, since it's the harsh winds combined with ice that cause mechanical damage to trees.
So now that we've gone into wind, let's look also at relative humidity. For relative humidity, we also hope to update the long-term records and bring it up to 2021. Relative humidity is a measurement of how much moisture is in the air. So when it's at 100%, that means that we're in a cloud, or that all the water in the air has saturated into droplets. So again, we wanted to look at trends over the years and assess the effects that they may have on vegetation. To do this, I first needed to calculate relative humidity using 3 different measurements: wet bulb temperature, dry bulb temperature, and pressure. The dry bulb temperature is your typical temperature measurement, but the wet bulb temperature is measured using a thermometer that has a wet sock on the bulb, which you can see on the right in that little diagram. And this is so that any evaporation that occurs will cause the temperature to cool slightly. But if the two temperatures are equal, then relative humidity is at 100% because all the water in the air has saturated. So the wet bulb and the dry bulb are essentially measuring the same thing. After a lot of troubleshooting with the calculations, I managed to get a list of relative humidities going back to 1941 and to update the long-term humidity records. So using the same years as the wind data, I calculated relative humidity throughout the seasons or the months. And we can see it's similar to Naomi's graph with wind, and that the summer months are generally seeing a lower relative humidity, which means more days that are in the clear, while the winter months have a much higher average relative humidity, meaning more days that are spent in the clouds. In terms of mechanical damage, that means that more damage will happen in the colder seasons because it's more humid, and so there's more potential for freezing fog, which is essential for mechanical damage. Over the years, we have seen barely any shift in relative humidity averages. As you can see in the plot, with the yearly average relative humidity on the y-axis, there's been no significant change from 1941 to now. The p-value and the sun slope indicate the same thing. And this can be seen as good news because it indicates that climate change has yet to affect yearly average humidities at the summit.
So now that we've talked about both wind and relative humidity trends individually, we'll talk about our initial attempts to combine these two variables to get a fuller picture of their effects on tree line. The way we did this was by looking at the frequency of damaging events where high winds occurred with fog and freezing temperatures. So for the purposes of our study, we considered events damaging when for any given hour, the temperature was below 32 degrees Fahrenheit, so freezing. There was fog, so high relative humidity, and the hourly wind average was above a certain threshold. We based these criteria off of case studies as well as previous studies on what wind speeds cause damage to vegetation. We examined a few different wind thresholds to try to capture different types of events, specifically events with over 25 mile per hour, 60 mile per hour, and 100 mile per hour hourly wind averages. And one big reason that cold, moist, windy conditions are so damaging is because they lead to the production of rime ice, which Larz will tell you about next.
So yeah, we keep on referencing rime ice, but what actually is it? So rime ice is formed from supercooled moisture in the air that solidifies on impact, leading to the formation of these long icicle-like features that grow into the direction of the prevailing wind. So here we have some supercooled moisture and wind. The supercooled moisture is actually liquid in the air, even though the temperatures are below freezing, which is very cool. But when it hits the surface, it solidifies instantaneously. So fog, freezing temperatures, and wind result in the formation of this rime ice, such as in this photo, which is from earlier this summer on an especially cold day. And we care about rime ice so much because it causes mechanical damage to trees through that quick accumulation and the freezing temperatures that cause abrasion to trees, which prevent growth, as well as causing limbs to break.
So overall, we've found little change in the frequency of events with fog, freezing, and wind over the years. These next few plots will show the number of damaging events each year since 1941. At this threshold, so filtering for events with 25 mile per hour or higher hourly wind averages, freezing temperatures, and fog, we have found a decline in the number of these events over the years. However, the implications of this shift is borderline. So the slope of the plot, while statistically significant, is negative 0.039, which amounts to roughly one less damaging event every 25 years or 10% less events every 100 years on average. This small downward shift indicates that the frequency of these events are declining. And then at the 60 mile per hour threshold, we found no significant change in the number of damaging events. At the 100-mile-per-hour threshold, we found no change again, but you'll notice that this plot has a lot of zeros along the bottom there that are skewing the send slope to 0. And this is because while, especially in winter, winds often gust to above 100 miles per hour on the summit, these wind thresholds are based off of hourly averages. And hours that gust above 100 often don't have an average above 100. So this data has a lot of zeros, which makes it hard to run the same stats that we ran on the previous slides. This is a good illustration of some of the challenges we've been facing as we work with this data set and how other statistical approaches should be explored. And we also need to look more into what exactly makes an event damaging and if we should adjust the thresholds we selected. But this project is still in its early stages, so this gives us a good jumping off point for where to go next.
So all in all, we've learned that fog and wind and freezing temperatures cause mechanical damage to trees, which defines, at least in part, where the tree line boundary is seen. The amounts of relative humidity and wind have not significantly shifted since 1941, according to our analysis. So we expect that the amount of mechanical damage that has happened each year since 1941 has also remained fairly consistent. But for the future, we need more research on what exactly makes a damaging event and how these events affect the tree line specifically. So I'm actually going to continue working on this project, so I hope to keep looking into some of these questions and get to the bottom of them. It's been really great to work with two different organizations, the Observatory and the AMC, and experience a collaborative project that is at its beginnings. I've learned a lot about how research projects are created and run, a lot about weather, a lot about the observatory, but most importantly, I've had a lot of fun.
And I'm going into my senior year of college, so I won't be continuing on with the project as directly as Larz, but I hope to stay involved on some level, and I'll definitely be taking the skills I've learned this summer with me going forward. I'll be doing an honors project conducting marine biology research over the next year. And while it's a different ecosystem, many of the research techniques, like figuring out how, what correct statistics to use, coding skills, and scientific perseverance are definitely applicable.
So we'd like to thank the Waterman Fund for sponsoring the project, Georgia Murray, Brian Fitzgerald, Jay Broccolo, Ken Rockcourt, and Eli Kester for all their help with this project.
These are our citations, and we can pass it back to Brian for any questions.
Mm-hmm. Brian, I don't think we can hear you.
Oh, what happened there? You hear me now?
Yeah.
Thanks. All right. Well, thank you so much. Thanks, Larz. Thanks, Naomi. Thanks, Henry, as well. Feel free, Henry, if you want to join us back. We'd love to get some questions here, get some answers from our speakers this evening. Again, if you're joining us through Zoom, feel free to use the Q&A button. We already got at least a dozen questions or so in the queue at the moment. So feel free, get those questions in. In fact, I already got some questions for all of you as well. Love those presentations. Well, let's get it going right away. So question actually first for you, Henry, if you don't mind. Certainly I had this question. Sandy, Lillian, we're curious as well. I know when you're talking about the average lapse rate, an average lapse rate and sort of away from mountains in the sort of free air, that generally it's 6 Celsius per kilometer. Can you give us a sense of what that's like in imperial units and Fahrenheit and feet and all that? Because I've always heard like 2 to 5 degrees Fahrenheit per 1,000 feet or something like that. Is that about average?
Yeah, I think it's like 3 per 1,000 feet, but I absolutely hate the imperial system. So sorry, but that is a very good point. And I'm looking it up right now.
Oh, that's okay. Well, I mean, I know it's a common question we get. In fact, I'm sure, Larz, you've probably heard it in the huts, people asking for like hiking weather information, Naomi when giving tours, any of that. I mean, people are always curious. So what is it, how much colder is it typically on top of Mount Washington, I guess, given, you know, an average sort of lapse rate on Mount Washington, either Henry or Naomi or Larz, if anyone wants to throw that one out there. What, 20, 30, 40 degrees colder than the valleys?
What, 20? So, well, that's what we're actually, I mean, kind of trying to figure out.
Yeah.
Technically speaking, it can be very variable. That's kind of the whole goal of the project. But yeah, I would say somewhere in the realm of 10 to 20 typically.
Yeah. Yeah, and certainly the Henry, you had showed the vertical temperature profile, part of the mesonet for the observatory, and that always gives such a nice visual of what that lapse rate looks like on, in real time. And so, yeah, from what I've heard, the 2 to 5 degrees Fahrenheit per 1,000 feet, and the reason part of that range is exactly what you're investigating. Oftentimes, the differences between having sort of those thermal blankets of clouds or any of that sort of stuff going on, the variation can be pretty significant, I'm sure, in different scenarios. Question. Oh, some really good questions here. Thank you everyone who's putting them in here. Great question from Karen. This might be kind of tough. I'm going to throw it out there. Feel free to say you don't know the physics on this one, Naomi and Larz, but Karen's curious, what conditions allow for water droplets to stay super cooled below that freezing mark? How is that possible? I mean, truthfully, it's hard for me to answer. Got anything? Because we were talking a little bit about it this morning.
Yeah, we were talking about it earlier, and the physics are confusing. But how I understand it is there's just something about water where when it's in its liquid form, unless it's touching something solid, it doesn't know how to become a solid. So when it's in the air and just floating around, it's able to be liquid still, but the moment it touches something,
yeah, it could be.
Yeah, I don't know
formation.
exactly the physics behind it, but I don't know if people have seen those videos online of when it's really cool and people will go outside with a water bottle and it'll be liquid and then they'll slam it and it'll freeze really quickly. It's kind of the same thing.
Yeah. Well, you can do your own experiments on Mount Washington, stand outside for long enough and you can see it yourself. And actually something I learned today from our former director of summit operations, Ken Rancourt, helped the project, talking about sometimes the color you see, the opaque whiteness, is that really quick phase change of all of that air suddenly being expressed only in that white color when it changes from that liquid water droplet to a frozen substance. That sounded pretty cool to me. Anyways, yeah, great question. Thank you very much for that as well. Question here from Doug, and this is actually going to be for you, Larz, related to, first of all, I think a shout out from Doug, who was a volunteer, I think at Lakes of the Clouds, who was doing naturalist talk. Curious, what other research has been going on down at Lakes of the Clouds? Because I know there's usually been a summer internship experience, a researcher at the Lakes crew, which is sort of unique to some of the huts.
Yeah, we're the only hut with a researcher. And we have 3 big projects going on, I guess. One is this one. One is the cloud catching project. So there's a cloud catcher down there, which I take cloud samples from. Essentially, it's a big box that condenses cloud water into a bottle that I collect. And that's been going on for about 30 years, if I remember correctly, and is related to acid rain research. So we're looking at the acidity and the pollutants, like nitrates and sulfates in that water. And then the third project is one that's going on throughout the huts. And all the naturalists are in on it. It's called Mountain Watch. Georgia Murray, who Henry referenced in his presentation, helped found that. And that is a plant phenology project. So we're tracking plants throughout the season, alpine plants especially, and seeing when they flower, when they bud, when they fruit, all of that.
Nice, excellent. Yeah, and certainly we've had Georgia present in Science in the Mountains in the past, and exciting to hear, especially from the long-term look at some of that atmospheric chemistry that at least the acid rain situation, one of those sort of environmental improvements that have been witnessed over time and even at elevation on Mount Washington, which is great to see. Question here, Henry, it's a tough one. I know we were talking a little bit about this when we were going through some of your presentation work before, but Pete is asking a question just generally, climate change versus lapse rate. So I know you referenced some of the climate change research and climate trends that have been investigated on Mount Washington. How does lapse rate come into the mix again when we're talking about the long-term changes of climate?
Yeah. So I had a feeling this could be a point of confusion. It's hard to explain quickly. So basically, a lapse rate is, or a temperature lapse rate, it's the change in temperature with elevation. And so imagine if you're looking at the lapse rate from the base of the mountain to the summit of the mountain, and say the summit of the mountain's temperature stays the same, but the base gets warmer, your lapse rate will become steeper. You'll have a bigger lapse rate. Say if the summit is 10 degrees and the base is 20 degrees, and you heat the base, the net lapse rate initially will be 10 degrees per that distance to the summit. If you heat the base then to 30 degrees and leave the summit at 10, then the lapse rate to the summit will be 20 degrees. And so if over time the base is warming more than the summit, then you will get a steeper lapse rate in that manner.
Thanks, Henry. That was helpful for me in trying to suss out some of those differences. And like you had referenced earlier from George's paper just last year, showing that the differences in the warming rates on the summit of Mount Washington versus even just down at the base of the mountain at Pinkham Notch, certainly a difference in that warming rate there. So who knows, the top of Mount Washington could continue to be a bit of a climate refuge, I guess, so to speak, in some ways, but may have an even bigger difference than it currently has down at the base, as I think you're referencing there.
Mm-hmm. We'll have to see.
We sure will. And since you're looking at a season here, I guess long-term goals, as I understand it, Henry, is eventually to not only look at what a seasonal or even a year or two worth of data, but pull it back even further to a full sort of climate normal period, at least 30 years or so. Is that correct?
Yeah. Ideally, you would want 30 years.
Excellent. Well, I have a question again for Naomi and anyone else like to jump in on this, but Andrew asked a great question related to rime ice and damage. So does rime ice cause damage to or affect the instruments at the summit that are measuring wind speed and humidity, especially since it damages trees so much? When you expect it to damage instruments? I know you haven't all been up there for a full winter or anything like that, but what do you know? What have you seen related to instrumentation on the summit?
Yeah, so rime ice definitely builds up quite a bit on the summit. But we have heated wind instruments that we leave up during the winter. So they're metal and they're actually heated. So the instruments themselves don't freeze up, but definitely the poles holding them up and stuff around them will freeze up. So in the winter and any time that there's icing, observers will go out once an hour, sometimes more, depending on how fast the ice is building up, and de-ice, which basically means taking a big mallet and knocking on all the ice for it to fall off so that it doesn't build up so much that it starts affecting the instruments.
Yeah, excellent. And I guess that's, I know from experience, the sling psychrometer is only coming out when you're not in the clouds, when there isn't rime ice occurring, because otherwise you don't need it. You can just use one of the regular thermometers in the shelter there. So thankfully that gets spared from some of the icing damage, hopefully, and doesn't get dropped. It's hard enough keeping that thing in good shape. Thank you very much for that. Lots of wonderful comments coming in here from folks here. Oh, geez. A great question. I have to ask because you did reference one of these papers before from Ken Kimball, who asks and states, trees can self-protect each other to be able to grow taller. Oh, interesting phenomena. Therefore, not only the number of damaging events, but maybe the annual interval between major events can also impact how well these trees can buffer each other and grow higher. Might this be examined in a future analysis?
For sure.
Yeah,
That's a really
definitely.
good point.
Yeah,
Interesting.
especially with like a local, so depending on where exactly things are located. So if there's an area with like big boulders that offer protection, or yeah, there's a stand of trees that can protect each other, there's definitely a lot of variation in how damaging these effects are. So that's definitely something to look more into in the future.
Yeah, and can you imagine using data from some other, say, of the observatory's mesonet stations at other elevations, even closer to tree line, to examine that as well?
Yeah.
Yeah, absolutely. Yeah. Yeah, we're starting with data on the summit because we have such long-term trends, and if trends are shifting on the summit, we can assume that they're also shifting on at tree line. But yeah, data actually from tree line would definitely be helpful.
Yeah, definitely. Yeah, some assumptions for a very complex terrain, obviously from the singular data point that we have here, but it's pretty solid for what we do have. So, all right, great question. I keep thinking now of Krumholtz being like penguins huddled around each other is the image I kind of keep having in my mind. Oh, question here, actually back around to sampling clouds at lakes. So the clouds for Larz, Pat asks whether any, Larz, do you know if any of the cloud samples are being analyzed for PFAS, those long-term synthetic chemicals that are starting to show up in all corners of society at the moment? Any
I am
idea on that?
not sure. I
That's a
imagine that if they are, it's like more recent and it wasn't from the start of the project, but it's definitely possible. I just send the samples down, so I don't know much about the analyzing.
well, and Georgia's joining the program and has already added a comment that I
Okay.
can see saying no PFAS yet, at least. Great question. Thank you. So this is a really great question from Kenneth, and one that I kind of had myself, and this is for everybody. So what do you wish you had experienced in your academic settings that would have helped you in your field work? What lessons have you learned that you might take back to the classroom? I know, Larz and Naomi, you kind of mentioned a little bit where you're thinking about in the future and all this, and maybe start with both of you. But I mean, so maybe focusing on the second half of that question, what have you experienced here that you definitely think you'll take back from the experiences so far in this internship, and how might that serve you not only maybe in the classroom, but I don't know, your career interests too? What are you thinking?
Yeah, so I think one of the cool things with this project is having been able to work with such a long-term data set, which is pretty unique. So that's been very cool. And then also just having to troubleshoot with the data set. I think in my where I'm going next, I mentioned I've learned some scientific perseverance, which I think is definitely true, because yeah, when you have something this complicated, sometimes the first thing you try doesn't work and you have to go to the next. And that's definitely a good skill that I'll be taking with me.
And I think I like just really starting a project with just like a bunch of data, messy data, that is, and like being able to slowly piece through it. And I feel like in school, I usually had like data sets that were pretty prepared for me, or like a project that was already going on. So like being able to just start the project was really cool.
That's great. And Henry, what about you?
Sort of similar to Larz. So this summer I did a lot of reading and working on the introduction to this project. And normally at schools, there's something that's cut and dry. Here's what you need to do. Here's what you need to find. But for this, I almost had to figure out what I need to find first, and then try to find it. And so I definitely learned a lot of valuable skills of just kind of organizing my thoughts relating to the project, and actually just learning to focus on just one section, and also finding things that are important and relevant, and tying multiple things together from different areas, because I wasn't just strictly looking at articles relating to temperature lapse rates, but I was looking for things relating to climate change and the alpine environment and how that relates. And So tying a lot of things together and just learning how to do that. I feel like that was what I really learned.
That's excellent. Thanks, Henry. Appreciate that. And I know we're running a little bit past 8 here, so just one last question for everyone, a fun one. Summer's coming to an end for the internships here for everyone, more or less. I'm curious if you all might just share, I don't know, favorite memory from this past summer, something that you'll hold on to for a little bit looking back. And Henry, I'll give you a second to think here, and Naomi and Larz, I don't know if you're brave enough to go first, but I don't know, happy memory thinking back to this past summer?
I have one. Well, working at the hut, I also have to do hut stuff. And one night, one crew member rallied the troops and we had a pit bull night. So we all dressed up as pit bull and introduced ourselves as Mr. Worldwide. And did dinner service that night. And that was actually the night that I met the new research fellow for the AMC. So Jordan was his name. I met him as Pitbull. So he has yet to meet Larz, but he did meet Pitbull.
That's a great answer, and boy, I had no idea what you're going to say there, so that's really good. Naomi, what about you?
Yeah, we were talking about this yesterday, actually, so it's a little fresh on my mind, but back in June, there was a night that the Northern Lights were visible, and the night observer tried to wake everybody up, was only successful in waking me up. So I went back to take a second crack at waking everyone up, and to mixed results, some people were happier than others, some people were more confused than others. And yeah, so that was fun, and I got to see the Northern Lights.
Oh, that's pretty special, even for observers who've been up there for a while. That's awesome. And Henry, what about you?
I think it's hard to pick. There was a lot of fun stuff that happened this summer. So if it's okay, I'll share 3 things.
All right, go for it.
My first week, I had like all the weather possible, from record-setting temperatures to thunderstorms to wildfires to icing and winds over 100 miles per hour. So that was really cool. And then in my last week, which is my second to last week, we had a variety show on the summit of Mount Washington, where we did everything from sing songs together to read poems about Mount Washington. And that was super fun. But I would be remiss also if I left out Lakes of the Clouds, because I made great friends with Larz and the rest of the crew down there. And there was one morning where I went down to play the Wizard of OBS, which is a nickname that they gave to me, and they do little theater productions, and I got to be involved in that, which was super fun.
Oh, that is awesome. That certainly makes me really happy. I'm so glad that you all had experiences like that, and somehow I can't believe I've never heard the Wizard of OBS before.
Yeah. We'll have to show it to you.
I would love that. Well, thank you so much, Larz. Thank you, Naomi. Thank you, Henry. Thank you for everything that you've given to the observatory and to your work at the AMC, and definitely all the fun and good spirits and enthusiasm that you brought to Summit Life this summer. We certainly appreciate your work and wish you all the best of luck in your future endeavors here. Thanks so much for speaking tonight. Thanks everyone for joining us on the program this evening. If you enjoyed tonight's free program, we do strongly encourage you to make a donation to support programs like these over at mountwashington.org. You can hit the donate button in the upper right-hand corner of the website there. And don't forget, a donation in any amount makes you a member of Mount Washington Observatory. If you have thoughts for tonight's program or suggestions for future ones, please take some time to fill out the Google survey form that'll open up in the Zoom window after this program, and in the follow-up email for everyone as well. And don't forget, if you'd like to join us for our next couple Science in the Mountains programs, the next one comes on Tuesday, September 13th, when Dr. Hannah Baranes from the Gulf of Maine Research Institute will discuss sea level rise and coastal flooding along the New England coast. And then join us again on Tuesday, October 11th. We'll be posting more about this program. We'll be welcoming back Dr. Peter Crane as we celebrate the 90th anniversary of Mount Washington Observatory's founding. So don't forget to register for those programs and watch any previous programs that you may have missed over at mountwashington.org/SITM. and we'll see you all again soon. Have a great night. Thank you all again. Thanks, Larz. Thanks, Naomi. Thanks, Henry. Have a great night, guys. And we'll talk to you soon.